Hello and welcome to Controllers Tech. This is the 6th video in the STM32 I2C slave series, and today we will see how the slave will send the data back to the master. In the previous video we saw the slave was able to save the data in the registers. Today we will program the slave to send the data back to the master. The video covers two different ways to do so. When the master simply requests to read the data, without mentioning the memory location to read from. And when the master specifies which memory location it wants to read the data from, and how many bytes it wants to read. We will continue where we left in the previous video. Here is the code from the Part 5 tutorial. Let's define an array and store the data to be sent. Just like our X count, define a variable to keep track of the number of bytes sent. Once the master initiates the request, the address callback will be called. We will write the rest of the code under the condition that the transfer direction is receive. Here reset the TX count to 0. And now call the sequential transmit in the interrupt mode to send 1 byte of data. We will send the data to send buffer, and the transfer option will be the first frame. This is the same as how we programmed the receive code. Once 1 data byte is transferred, the slave transmit callback will be called. Here we will increment the TX count variable, so that the next byte is the buffer can be transferred. Now send 1 byte again, but with the option of the next frame. Let's build and debug the code. Let's add the TX count variable to the live expression. I2C read will simply request 4 data bytes from the slave. Here we have received the data. This is the same as what we defined in the buffer to send. Let's read 6 bytes now. We have received the entire buffer. This looks a bit confusing, so let me change the data in the buffer. Let's read the 6 bytes again. Now you can see the data received is the same as what we defined in the buffer. Note that the TX count is 7. Each time the callback is called, the TX count gets incremented. So when the last byte is transferred, the callback is called again, and the TX count gets incremented again. This makes the value of TX count 1 higher than the actual data bytes sent. Let's try to receive 10 bytes. We received the 6 bytes as per the values defined in the buffer, and the next 4 bytes are random data. This is basically the data stored in the next memory location where the buffer is stored. Now let's talk about the errors. No matter how many bytes the master requests, there will always be the error, the acknowledgement failure error. Since we don't know how many bytes the master has requested, the slave transfers 1 byte each time the master sends the acknowledgement. When the master sends the NAC response, it acts as an acknowledgement failure for the slave. Here the error code will be 4, and this is the same what we get while the slave is receiving data. So we need to make a check for whether the slave is receiving, or transmitting the data. After encountering the error, we will first clear the error flag. Now we will check the TX count variable. If the TX count is 0, it means that the slave never transmitted the data, and hence the error must have occurred while receiving. And in that case, we will call the process data function, same as what we did in the previous video. But if the TX count is not 0, that means the error must have occurred while the slave was transmitting. In this case we will reduce the TX count variable by 1. Remember I mentioned earlier that the TX count variable ends up at 1 higher value than the number of bytes actually transferred. So here we are correcting it. Let's build and test this now. I am putting a breakpoint in the process data function to check if it gets called. We have received 10 bytes of data. The TX count value is 10, there was an error but the process data wasn't called. So this is working fine. The function I2C read is similar to using the function HAL I2C master receive. Here we mention where the data will be stored, and how many bytes the master wants to read. It does not specify the memory address in the slave, instead simply requests the data. The interrupt or DMA versions of the same function can also be used for the master. So we saw how the simple read operation can be performed on the slave. Now we will see a bit more complex read operation, where the master specifies the memory location. The function memRead can be used by the master for this purpose. Here the master specifies the start register it wants to read from, and how many bytes it wants to read. In the slave file, we have already defined the registers. We will treat these as the memory registers for the slave. Let's understand how the slave will receive the request from the master. The read from function is the same as the memRead function we just discussed. Here the master is requesting 3 data bytes, starting from the register 5. It received the data, as we haven't modified the code yet, and the slave is still sending the data to send buffer. If you look at the RX buffer, you see the first byte holds the address of the register the master has requested to read from. I am hoping that you already have an idea about how the protocol actually works here. The master first writes the register address it wants to read the data from. This address gets stored in the first byte of the RX buffer. Then the master sends the restart condition with the read request. Since the process starts from the beginning, the address callback is called again. The transfer direction is received this time, hence the slave will transmit the data. Let's create a variable to store the position of the start register. This time we are transmitting the data from the I2C registers. Update the position variable with the register address. And then use the register address as the offset while transmitting the data. Let's build and debug this now. First the master is writing the data into the registers. Let's add the I2C registers to the live expression. Here you can see the registers got updated with the new data. Now the master is reading 4 bytes, starting from the register 3. We got the data, 6, 5, 4, 3. You can see the data is exactly the same as stored in the registers, starting from register 3. Let's try reading 4 bytes, starting from register 5. Here we got the accurate data again. Let's read all 10 bytes, starting from register 0. We got the data again, and this is the same as what's stored in the registers. So the slave driver is working very well. We saw how the master requests the data from the slave, and the slave send that data accurately. This is it for this video. I hope you understood how to program the slave to respond to the read request. In the next video, we will see how to handle some common errors in the I2C. The link to download the code in the description of the video. Leave comments in case of any doubt. Keep watching, and have a nice day ahead.